Hey, I'm Austin Hutchison, and this is my video report for Lab 4 about oscillations. The purpose of this lab was to use Tracker to analyze the oscillating motion of an object attached to a spring and then compare it to a Python model that predicts that motion. Then I computed and plotted the changes in each energy type in the system. A little preview of the results. The computational model graph was pretty accurate in predicting the oscillating motion of the object, but was very slightly off. The total energy change in the model stayed at zero throughout the time period, since all the energy changes cancel each other out and sum to zero. Here are the main physical principles that we're going to be using in this lab. First is Newton's second law. The velocity and position update formulas can both be derived from that, and those are obviously going to be useful in our calculation loop. And we're also using the oscillation period formula, T equals 2 pi times the square root of m over the spring constant K. That's going to be used to calculate the spring constant, obviously, and then the spring force and spring potential energy later on. We're using the conservation of energy principle, delta E equals delta K plus delta U. Obviously, since this is an isolated system, delta E is going to be zero for the whole thing. So delta K and delta U should just be opposites of each other for each part of the system. And then translational kinetic energy is just the kinetic energy formula, 1/2 mv squared. Change of potential energy of gravity is the mass times gravitational force times the height of the object. And then spring potential energy is 1/2 times the spring constant times s squared, where s is just the difference between the current length of the spring and the relaxed length. And these three are the types of energies that we're going to be accounting for in the system for this lab. For the details of the experiment, for this lab, we're taking the system to be the weight attached into the spring itself, and the earth. And since these are the only objects that are going to have any real effect on the energy, the surroundings are just nothing. The mass of the weight is 0.402 kilograms. The initial position is this, and the initial velocity was 0. And I calculated the spring constant and the relaxed length of the spring, both using the oscillation period formula from the last slide. Moving on to the actual Python model, here in these first 5 highlighted parts, I just inserted the values that were either given or that I calculated. Like for the spring constant and the relaxed length of the spring, L, which just represents the stretch spring at a given time, is just the end of the spring position vector minus the origin vector. And then S is just the magnitude of that vector minus the relaxed length of the spring. And of course, here is just all the formulas for each type of energy, and total E is 0 because it's an isolated system. This next part of the model is basically just a loop that works on each data point. Here it just uses the formulas for gravitational and spring forces and then adds them up to get the net force here. And line 124 and 126, it just applies the velocity and position update formulas. And down here, it calculates the change in each type of energy by just subtracting the initial value for each from the current value. And of course, delta E is 0, again, because it's an isolated system. Now let's compare the model graph and the observation graph. They both look very similar, but the model does seem to be more accurate in predicting the x position than it does for the y position. Also, in both graphs, it seems to diverge from the observation graph more and more as time goes on. As you can see down here, it gets further and further from the red. And some potential sources of error that could cause this is inconsistency when tracking the position in Tracker. Like, it may not have been exactly at the center of mass for each frame. And also not accounting for forces other than gravity or spring forces, like drag or some other hidden force. Here's just a picture of the final path that the object took during the time interval in the model. And right here's the energy graph that shows all three types of energy, and then the total, the delta E in the middle, which is obviously 0 throughout the entire model. So now on to the discussion questions. Is the energy principle satisfied? I would say yes, because all the energy changes in the system sum to 0, meaning no energy is being added or removed from the system. It contains the weight, the spring, and the earth, so there are no surroundings that can do work on it. Next, I compared the oscillation periods using the x and y position data, and I found that the period using x was 1.615 seconds, and using y was 1.52 seconds. Which one you choose to use affects the calculation of the spring constant, which in turn affects the calculation of the spring force and spring potential energy. This could be due simply to human error or the way tracker interprets the oscillation movement. And that's pretty much it. So thank you for watching.